Okay, so the next one is the problem concerning the quantized energy level of an electron bound to a hydrogen atom. And there's a Bohr's atoms and the energy levels are quite well defined. And so the question is use the what is called the Redberg Equation and determine the energy level difference between fourth and the first energy level. So n is 4 and n is 1. What's the energy level differences for a hydrogen atom? Okay, and this is an equation you will be able to find out in the reference sheet, where the energy of quantized energy level, depending on the levels, which is an n, and then they are proportional to just the equation just looks like that. And where you can find this equation, and then so you don't have to memorize this. Let's go back to the reference sheet. So this is a reference sheet and will be given out, and then if you look carefully, there are two equations that is related, and this is an equation that I just show it to you, and it says a hydrogen atom. So as far as the hydrogen atom, the electron bound to the hydrogen atom is quantized at this discrete energy levels depending on the numbers of n. That's what it is. But there is another equation that's shown up here, which is here. This is using the RH. That's a Redberg constant for particularly hydrogen case. And this is this equation can be used. So in this one, the equation is shown energy is quantized, but energy differences actually can be shown as an inverse of the wavelengths of the light. And this is essentially the same equation. It just has a different historical origins for those who find out this equation. So let's use these two equations to solve the different aspects of the problem. Okay, so to have a better visualization and a better understanding of this energy level, I'd like to show you this diagram. Okay, so first of all, this energy is a negative, right? So this is when this is a negative means electrons are bound. So this is a 0. That's an energy level. When it's positive, we talked about in the photoelectric effect, they have a kinetic energy to move around. All the electrons are bound here, and the lowest one is an n is 1, and the second one is n is 2, and you can see an n is 3, and n is 4. So and that the levels are getting the spacing is getting very, very small. Eventually, it's just getting like this. And you can see this when n goes infinity, En goes to 0, right? And this is where the electrons start to have a highest energy. They start to be escaping out of the bounded electrons. Okay, so what is the energy differences? So therefore, the A is essentially when you have electrons here and when you have electrons here, what's the energy difference is? So this is a delta E, right? So delta E is minus 2.18 10 to the minus 18, and then this and n is 4 has a higher energy than this one, so higher energy, which is 4 square minus 1 square. Okay, and that will be in the unit of a joule. Okay, when you ever do that, and then you'll get this energy level differences. That will be a positive, okay, 2.043 10 to the minus 18 joule. Okay, so I can get this. So let's get I will give you the one more time to give you the more simplistic view. So this is an energy level diagram. That's an energy. This is zero level, that's a positive, and this is a negative. Negative, once again, is a bounded electron. We are talking about n is 1, and this is somewhere n is 4. And the energy difference, level difference is delta E. And this is what we just calculated here, right? And if you look at that, this is this energy level difference is sort of the opposite of the photoelectric effect. The photon can be released, h nu the photon can be released in the form of an energy when the electron with higher energy essentially was dropped to a lower energy state. Okay, so when this higher energy state drop, this energy will be essentially released in a form of a photon, and that has a unit of h nu. And we are more interested in not knowing about frequency but the wavelengths of the light. So c over lambda, and the lambda is the wavelengths of the light, right? So the concept here is, so delta energy is h c over lambda. So this is a proportional to 1 over lambda, right? Other than that, Planck constant and the speed of light is just a constant. So that's why, if you remember, let's go back to one more time. If you look at this equation shown up here, right? This 1 over lambda is nothing but just a new form of an energy differences, and this is what is shown as a Redberg constant. So you guys have two options to solve this problem. Using these energies and using the Planck constant and speed of the light, you can calculate the lambda, or you can do the shortcut, which is essentially using this 1 over lambda is an RH, because this is equation is given here, and then the n1 square minus n2 square, right? So therefore, and then the RH is 1.0968 10 to the 7 inverse meter, right? So that's a matching unit, which is a inverse meter of the wavelengths of the light. So 1 over lambda is now RH. So energy level difference is between 4 and 1. So here you want to say 1 square minus 4 square, the Redberg constant, and then you plug it in, 0.0968 10 to the 7, and then this is a 1 over 1 minus 1 over 16, right? And that's the inverse meter. And eventually, when you solve this, the lambda that you will have is 9.723 10 to the minus 8 meter. In terms of the length scale in the electromagnetic spectrum, it is typically people use a unit of microns or nanometers. So I prefer to use, let's try to convert this into a nanometer, right? So this is same as 10 to the first multiply 10 to the 9 meter. So therefore this is same as 79.23 nanometer. So 10 to the 9 minus 9 meter. And this is essentially ultraviolet UV region. If you're looking at the table and of the electromagnetic spectrum, and that there will be, by looking at this, the answer for this is C, for the third portion, section of electromagnetic spectrum, the answer is UV. Okay, if you look, and the figure has to be provided, you can look at the figures in the textbook.